In this video, we will discuss the concept of wave-particle duality in more depth. Let's quickly review what we've learned about the behavior of light so far in the past two videos. First, we know that light behaves as a wave. It shows interference effects, which is characteristic of all waves. But we also know that light can behave as a particle. We know that from experiments and observations regarding blackbody radiation and the photoelectric effect, both of which we discussed in our last video. We also have evidence for something called the Compton effect, something that we have not discussed thus far, which involves a process of momentum transfer. And very simply, this involves an experiment in which a photon, a quantum or packet of light, impacts an electron, and we observe the electron moving in a particular direction after the collision with a momentum me, the mass of the electron times its velocity. So P here represents momentum, and you'll see that that's a symbol we're going to typically use for momentum. So P is equal to the mass of the electron times the velocity of the electron. And the photon is scattered off the electron moving in some direction as well. Now, without going into the mathematical details here, we know that conservation of momentum must hold. That is, the total change in the momentum must be equal to zero. And based on observations and collection of data from these photon-electron collisions, and what's called the Compton effect, we can determine that the photon momentum is equal to h being Planck's constant, divided by the wavelength of the photon. Now, of course, we know that photons have zero rest mass, so this is certainly different from a classical expectation. Classically, a particle which has zero mass would have the zero momentum. But in this circumstance, these observations seem to indicate that the photon, and it does behave as if it's a particle colliding with an electron. We see scattering of the electron, we see scattering of the photon, and the photon momentum in these particular experiments can be determined as equal to h divided by lambda, lambda again being the wavelength of the photon. So this idea of photon momentum gives us an equation for the momentum related to inversely proportional to the wavelength of the light. All right. So the question that arises is, we see that light can behave as a wave under certain circumstances, and it can behave as a particle under other circumstances. Is it possible that what we conceive to be particles, such as electrons, can, under the right circumstances, behave as waves? In 1924, Louis de Broglie proposed that, yes, particles do have a wavelength. He did this in his PhD thesis, by the way. And that just going with the concept that we discussed earlier, momentum, of course, P being equal to mass times velocity, and knowing that in the case of a photon, that momentum is equal to h over lambda, de Broglie just simply said, well, if we rearrange that equation, and here we're talking about just simply solving for lambda, that the wavelength is equal to h over p. So de Broglie suggested that particles should have a wavelength that's inversely proportional to their momentum. And again, reminding that momentum is mass times velocity, we're going to certainly see that particles that have large mass will have, because of their large mass, have a large momentum, would have a very small wavelength. So this is going to be most important for particles with very small mass, such as an electron. So that was de Broglie's proposal. Experimental evidence that supported de Broglie's concept of the wave-particle duality came first in 1927, an experiment of Davison and Germer, in which they took an electron beam and directed it at nickel crystal, and then looked at the electrons that were then scattered from the crystal surface. What they noticed was this alternating pattern of bright, dark, which of course is characteristic of interference effects. So here we have a situation where electrons are diffracted from crystals, just as light waves are diffracted from crystals. You may be aware of the fact that we use X-rays and X-ray crystallography. We shine X-rays on crystal surfaces to help determine structure. And again, the scattering of those X-rays generates an interference effect, just as we see the scattering of an electron beam generates an interference effect. So here we see evidence of what we thought were particles, electrons, behaving as waves. We'll also observe these kinds of interference effects in the classic double slit experiment. If we take a beam of electrons and shine it through double slits, we will notice the characteristic interference pattern under the right circumstances, as we see right here on this. So we do have evidence then from these experiments that electrons do behave as waves, and small particles in general. We'll certainly see interference effects. Right circumstances. Well, this begs the question. Suppose we do our double slit experiment where we use a source of particles that emits only one particle at a time, say an electron, for example, in this particular case. We take these electrons and we direct them through what is essentially a double slit. It's a little bit more complicated than that in the case of electrons. And then we look at the pattern of electrons that we generate. We would certainly expect that if we take a single electron at a time going through the slit, we will notice that it either goes through one slit or the other. Certainly an electron can't go through both, right? So we take a look at this pattern. And we take 10 electrons and we shine it through the double slit, and what we see here first is just what seems to be a random pattern of 10 electrons having passed through the double slit. You see the little bright dots there, they correspond to electrons impacting the screen. And after 100 electrons we just see more of that same kind of random pattern. 3,000 electrons, 20,000 electrons, and you may begin to see something emerging here. After 70,000 electrons, we can clearly see an interference pattern where we have bright, dark, bright, dark. All right, so we're seeing interference, we're seeing behavior of these electrons as a wave. Okay, but the big mystery here is, how does that happen? How is it that when we take one electron at a time and we shine it through these double slits, surely that one electron only goes through one slit. How does it know where to go so that after 70,000 electrons we do have an interference pattern? What's it interfering with? How can it interfere with itself? This poses a significant philosophical conundrum about, and our concern here is, what does it say about the nature of reality? Do these electrons pass through one slit or the other, or does an electron pass through both? What can we say? Well, there are many different ideas about what's going on here, and Bohr essentially said, well, we can't really say what's going on because all we can say is this is what we observe. We can't, in the absence of observation, we can't really say anything about what's going on. This is something we'll talk a little bit more about if we have time, but regarding chemistry, it doesn't have a significant impact on what we're doing. The most important thing to take from this is that electrons can behave as waves, or they can behave as particles. Light can behave as waves, or it can behave as particles. We will find that we'll see wave-like behavior when we try to measure wave-like behavior. We'll see particle-like behavior when we try to measure particle-like behavior. For example, in this double slit experiment, if we were to ask the question and try to measure which slit the photon or the electron goes through, that process of actually measuring a particular opening and determining which slit it goes through destroys the interference pattern. It disappears. So it's as if the particles are somehow aware of what we're trying to measure and give us the corresponding result. And that's what we will see. If we try to measure a wave-like pattern, wave-like result, we'll get a wave-like result. If we're trying to measure something that's particle-like, we'll get a particle-like result. So we have this important quality of wave-particle duality. And from our perspective as chemists, the most important thing is to acknowledge that it's going to sometimes behave as a wave and sometimes behave as a particle. One important consequence of this wave-particle duality for electrons, you may think, well, what's the big deal? How does it have practical consequences? Well, electron microscopes, the concept of an electron microscope is certainly due to this wave-particle duality on the part of electrons. Optical microscopes we can obviously use to observe things that are very small, but we start to run into problems. How well we can resolve a particular image depends on the wavelength that illuminates that image. We're unable to resolve things that are smaller than the wavelength of the light, of whatever we're using to illuminate it. For example, knowing that visible light runs from 400 to 700 nanometers. If we're using an optical microscope, that means if we're trying to look at something that's smaller than a few hundred nanometers, we're not going to be able to resolve it with optical light. We have to have something which is much smaller in wavelength than that. So electron microscopes serve this purpose because when you accelerate an electron through a potential difference V, a voltage V, we're going to be able to generate really small wavelengths. So let's just go through the derivation here. First, we know that if we have an electron that's moving with speed v, here the little v in this particular equation, that its energy is 1/2, kinetic energy is 1/2 mv squared, and this is going to be equal to E times v when we direct it through a potential difference. Again, v being the voltage, E is the charge of an electron. So just to be clear here, the charge of the electron E is 1.6 times 10 to the minus 19 coulombs. So if we take the potential difference of voltage and multiply it by the charge, we get something which actually turns out to be in units of energy. The thing to remember here is that a volt, 1 volt is equal to 1 joule per coulomb. So if we take the number of volts and multiply it by the number of coulombs, then we get joules as our energy. So that's important to note here. Now, of course, we remember that momentum is equal to m times v, v again being the velocity here. So small v is velocity, big V is voltage in this case. We also can show, just through mathematical arrangement here, the relationship between kinetic energy and momentum, that kinetic energy is equal to the momentum squared over 2 times the mass of the particle. We also know that the wavelength of the particle is h over p. And again, since p squared is equal to, p squared over 2m is equal to the energy, that's equal to E times v. And we can solve for the momentum as being equal to this relationship here, the square root of 2me times E times v. So, substituting this expression for p into our expression for lambda, we get a simple relationship here which shows the wavelength of an electron accelerated through a potential difference v given here, and we can calculate then the wavelength of that electron. Now, in electron microscopes, the voltage tends to be very, very high, on the order of tens of kilovolts, for example. So one thing you are to do associated with the worksheet for this particular video is then to calculate the wavelength for an electron accelerated through a potential difference of 50,000 volts. And you'll find that this wavelength is indeed very small, much smaller than that which is associated with optical light, and that very small wavelength then allows us to image smaller objects than would be possible then through optical microscopy. So that then ends our discussion of the wave-particle duality issue and how clearly classical theory cannot give us an appropriate explanation for these observations. The last particular observation that we're going to discuss here that seems to indicate deficiencies in classical theory is that very simply of line spectra. You know from past chemistry classes that if you take an electron discharge tube or a discharge tube containing some gas like hydrogen gas is indicated here in this particular tube, and you take the light emitted from that discharge tubes connected to a high voltage source and use various you'll find various dispersing elements, you'll find that the light emitted contains very discrete wavelengths. This is an experiment you did in general chemistry, and it's one which we'll repeat in the lab associated with this class. So you'll see what we call spectral lines. The dispersing elements that are used in these that separate out all the different colors in the emission lines might be a diffraction grating or a prism that separates the different colors. And so we do see these, as I mentioned, these discrete lines. And it's really, this is something that explains colors, that we get these discrete lines. That's why different substances are different colors, because they don't emit or reflect or absorb all wavelengths of light, but only very specific ones. If all the light, if all the wavelengths of the visible spectrum were emitted, then we'd just see white. Or if all the wavelengths of the visible spectrum are absorbed, we would see black. We wouldn't have colors if they were all emitted or absorbed. So the fact that we only get certain colors emitted or absorbed explains why different substances have different colors associated with them. So this is obviously a very common observation, but classical theory could not explain why we have these discrete colors or discrete lines in our spectrum. So let's take a little bit more deeper look at the hydrogen emission spectrum. If we take a hydrogen lamp and we look at the visible light emitted, we're going to see four visible lines. Here you can see these four lines. You have one here that's violet. This is kind of a blue-violet. These are the wavelengths in nanometers. At 486 nanometers, we have one that's kind of a blue-green color, and then way up here at 656 nanometers, we have a red line. So we look at the hydrogen emission spectrum, and this is what we see, just these four colors emitted, and that explains it. So that's what we observe. So the question is, how is that the case? Well, we can explain it by using energy levels, by looking at this situation where the electrons can exist within the hydrogen atom in discrete energy levels, which are given numbers here ranging from 2 through 6, and then of course up to infinity. Of course there is one lower that would correspond to a number 1, but it turns out, as we'll see, that one doesn't correspond to any visible light emitted. So in this situation, then the colors of the light emitted depend on transitions between these energy levels. So that we'll note that in this particular case, the hypothesis that these levels exist can explain then that violet line that we see corresponds to a transition going from level 6 to level 2. Right? Clearly, the electron loses energy when it goes from level 6 to level 2, and that loss of energy is what gives us the energy of the photon that's emitted, so that the lost energy, which we'll call delta E, is going to be to the energy of the emitted photon, which we know from our past discussion is equal to h nu, where nu is the frequency of the photon, or in terms of wavelength, it's equal to hc over lambda. So that violet color, the wavelength corresponding to that violet line, allows us to determine the energy difference between level 6 and level 2, as indicated in this diagram. Now, historically, Rydberg was actually determined an equation that corresponded to these emission lines. Wavelength here, 1 over lambda being the wavelength of the line emitted, is given by this particular expression, where N1 corresponds to the number of the lower emission line, and N2 corresponds to the higher, the higher energy level. So N1 is the lower energy level, N2 is a higher energy level. The wavelength of the emission line that can be calculated using what's called the Rydberg constant. Let me write that out here. Which is only applicable to hydrogen, by the way. So for the hydrogen atom, we have this equation that relates the wavelength emitted to the upper level and the lower level. So, for example, again, this violet line here would correspond to an emission. The wavelength of that violet line is equal to R sub h, and again, the lower level here is 2, so that's 2 squared, minus the upper level, which is 6, so that's 6 squared. So that wavelength, which is given above at 410.1 nanometers, is given by that equation. Now, I will add, you have to be careful here in doing these calculations. Be very careful about the units, because the Rydberg constant is in inverse centimeters, and I've indicated the wavelength here as being in nanometers. Obviously, you're going to have to do some unit conversion in order to do this calculation appropriately. The centimeters have to be converted to nanometers, or vice versa, in order for this to work out. If we want to express this in terms of energy, we will note that 1 over lambda, of course, is proportional energy, because energy is equal to hc over lambda. That energy difference between those levels then requires that we just simply multiply by the additional factor of hc in order to do that. Again, watch out for units when you're doing these calculations. If you want energy to be in joules, then we'll have to note that C has got to be in meters per second, and you're going to have to convert the Rydberg constant to inverse meters in order to do the calculation. Again, as we'll talk about using MathCAD to do these calculations, MathCAD can actually handle these units correctly. All right, so we've got these levels. What's the explanation for these levels? Well, this is where Niels Bohr, first in 1913, 14, in those particular years, came up with this model of the atom to explain the levels and explain the transition. He very simply just said, well, we've got discrete orbits in this model, and that the emission lines that we see in the spectrum correspond to a transition from an outer orbit to the inner orbit. So again, when we look at that 410 nanometer line, that violet line in the previous slide, that's going to correspond to the situation where, and actually there's a mistake here, that's going to correspond to the situation where we're going from n equals 6. Now if we count here, in this case, here is orbit 2, and orbit 3, orbit 4, orbit 5, orbit 6. So the 410 nanometer line that we see in what's called the Balmer series, that violet line, corresponds to a transition from the outer orbit here at n equals 6 to the inner orbit at n equals 2. So emission lines occur when we go from an outer orbit, the electron goes from an outer orbit to an inner orbit, which also corresponds to higher energy, lower energy. The outer orbits are at a higher energy than the inner orbits, because the inner orbits are closer to the nucleus. Because they're closer to the nucleus, then we see the situation where the outer orbits are at higher energy and the inner orbits are at lower energy. And again, the energy difference between the two is going to allow us to calculate the frequency and the wavelength of the photon. Now, again, this idea of discrete orbits was inconsistent with classical theory. One of the things about classical theory says that if you have an accelerating charged particle, it's going to emit electromagnetic radiation. An electron traveling in a circular orbit, as indicated here, is accelerating. When you change the direction, of the motion, you're changing the velocity, and therefore you're going through an acceleration. So an electron traveling in a circular orbit should be emitting electromagnetic radiation, which also means it should be losing energy. And so what should happen is, as it loses energy, as it's traveling in this circular motion, we should find its orbit decaying, and eventually it's just going to spiral into the nucleus. The idea of an electron traveling in a circular orbit about the nucleus classically is unstable. It should not be allowed. The electron would just, according to classical theory, spiral right into the nucleus, and the whole system would collapse. Bohr's concept of discrete orbits, basically, he said because the electrons can only exist at certain orbits, it can't spiral into the nucleus. It does not spiral in the nucleus, and so it is stable. And that was his simple answer. There's no classical explanation for it. He just said this is what it is. It is stable in these discrete orbits. The electron can only exist in these orbits. It cannot exist in any other orbits, and it will not spiral into the nucleus. This is clearly not classical, nor is it intuitive. It doesn't make sense based on the concepts at the time. And this is, as you're going to see over the next few weeks, one of many very, very non-intuitive results associated with atomic behavior that violate the principles of classical theory. There's stuff that we're going to find out that just doesn't make sense. So here we are right now. We have, in this particular video, talked about wave-particle duality. We've talked about discrete emission lines that we observe in the spectra of specific atoms. And we find that there is no way to explain these classically, which means we need a new theory. Niels Bohr developed this orbit model of the atom, which actually works perfectly for the hydrogen atom. We'll find that actually this theory that Bohr developed does not work when we start talking about other systems, that it is inadequate, and we're going to have to develop something beyond this. And this will lead to the development in the mid-1920s of what we know as quantum mechanics. And we'll begin discussing that in our next video.